Hello, in this lecture we'll find out the radius of a circle using two different methods. In the drawing we have a circle. We know that the center of the circle is at point O. Line segment AB equals to 6 units. Line segment AD equals to 18 units. Line segment CB or BC equals to 13 units. Angle PAC, this angle equals to 90 degrees, and also angle ABC, this angle equals to 90 degrees, and our mission is to find out the radius of this circle. So first of all, we'll make a construction. We'll start with the first method also, of course, and we will make a construction. From point C we draw perpendicular on AD. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. So actually, in quadrilateral A, B, E, C, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. The sum of 3 right angles is 90 times 3 is 270 degrees. In order to complete the sum of angles in this quadrilateral ABEC to 360 degrees, the fourth angle must be also equal to 90 degrees. So quadrilateral ABEC is 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. Therefore quadrilateral ABEC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. AB equals to EC, but we know that AB equals to 6, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE. But we know that BC equals to 13 units, therefore AE must be also equal to 13 units. Okay? And what is the length of ED? From the drawing it is very easy to see that line segment ED equals to AD minus AE. Again, AD minus AE equals to ED. AD equals to 18, AE equals to 13. Therefore, ED equals to AD minus AE, that is to say 18 minus 13, that is 5. So ED equals to 5 units. In the next step, we'll join points D and C together by a straight line. By joining points D and C, we created a triangle, the small right triangle ECD. In the small right triangle ECD, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ECD, by PT is a version for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DC, therefore the square of the hypotenuse is DC squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to EC squared plus ED squared. Repeat again, according to the Pythagoras theorem, in the right small triangle ECD, DC squared equals to EC squared plus ED squared. So DC squared, that is the square of the hypotenuse, must be equal to EC squared. EC equals to 5, therefore EC squared, EC equals to 6, yeah. EC equals to 6 units, therefore EC squared equals to 6 squared, that is 36, plus ED squared. ED equals to 5 units, therefore ED squared equals to 5 squared, that is 25. So in conclusion, we found out that DC squared equals to 36 plus 25. 36 plus 25 is 61. So we found out that DC squared equals to 61. We'll take out of this equation and we'll get that DC equals to the square root of 61. So here we can write down that DC equals to the square root of 61. In the next step, we will join points B and D together by a straight line. By joining points B and D, we created the right triangle ABD. So we'll implement the Pythagoras theorem on this right triangle ABD. On the right triangle ABD, by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle is BD, therefore the square of the hypotenuse is BD squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to AB squared plus AD squared. In conclusion, we found out that according to the Pythagoras theorem, in the right triangle ABD, BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse in the right triangle ABD, equals to AB squared. AB equals to 6, therefore AB squared equals to 6 squared, that is 36, plus AD squared. AD equals to 18, therefore AD squared is equal to 18 squared, that is 324. So in conclusion, we found out that BD squared equals to 36 plus 324 is 360. Here we take out of this, but first of all, we know that BD squared, it is equal to 36 times 10. So we'll substitute 360 by 36 times 10. So BD square equals to 36 times 10. Now we take out of this equation and we get that BD equals to the square root of 36 times 10. Here we will take 36 out of the root. The square root of 36 is 2, so it's 6. BD equals to the square root of 36, that is 6, times square root of 10. So in conclusion, we found out that BD, that is the hypotenuse of the right triangle ABD, equals to 6 times square root of 10 units. Okay. In the next step, we'll calculate the area of triangle BDC. This is the green triangle, is triangle BDC, and we'll calculate the area of this green triangle BDC. According to the formula, the area of any triangle especially of the area of triangle BDC. Here the square brackets is the sign for the area. It means the area of triangle BDC will be equal to the base of the triangle times the height to the base over 2. Okay? So the area of triangle BDC, we choose the base of triangle BDC, the green triangle is BC. This is the base. So the area of triangle BDC will be equal to the base, that is BC, side BC, the name from side BC, times the height. I will return and say that the height to the base must create 90 degrees with the base. Point B is on BC, point C is on BC also. So the only vertex that we can draw perpendicular on the extended BC is from the vertex D. So from the vertex D of the green triangle BDC, we will draw perpendicular on the extended BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and the extended BC as F. In the next step, we will focus on quadrilateral ABDF. In quadrilateral ABDF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, therefore the fourth angle must be equal to 90 degrees in order to complete the sum of the angles in quadrilateral ABDF to 360 degrees. The missing angle, that is to say this angle, must be equal to 90 degrees. So in quadrilateral ABDF we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral ABDF as a rectangle. With a rectangle, quadrilateral ABDF is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle ABDF, AB must be equal to DF. AB must be equal to DF. But it is given us in the question that AB equals to 6 units. Here AB equals to DF according to the rule that the opposite sides of a rectangle are equal to each other. It is given us in the question that AB equals to 6. So from this equation, 6 is equals to AB equals to DF. We will derive that DF is also equals to 6 units. So here, the IDF is equal to 6 units. Okay. Now you can calculate the area of the green triangle BDF. As I already mentioned, the area of triangle BDC the green triangle BDC, the area of the green triangle BDC equals to the base times the height over 2. That is to say, the area of triangle BDC equals to the base, that is BC. But it is given us the question that the that the base BC equals to 13 units. So we substitute the base by 13 times the height. We only found out that the height, df, equals to 6 units. So it is 13 times the height, that is 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So we found out that the area of triangle BDC is equal to 39 square units. Okay. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. According to the new rule, this will be rule number 1. If a triangle, that could be any triangle, is blocked by a circle, if a triangle is blocked by a circle, then the radius of the circle that blocks the triangle is equal so first of all I will draw the circle with the triangle that is blocked by it, and then we'll see the formula for the radius. We have this circle, in this circle we have the triangle ABC that is blocked inside the circle. This is triangle ABC. A. The vertex A touches the circle B and C. And we know that the length of side AB equals to A units, side BC equals to B units in its length, and side AC equals to C units in its length. And we define the radius of this circle. O is the center of the circle, M is the point of the circle itself. The radius of M equals to capital R, according to our definition. So the value of capital R will be equal to the multiplication of the side lengths of the triangle by each other, that is to say A times B times C, over 4 times the area of triangle ABC that is blocked by the circle. I'll repeat again, if we have triangle ABC that is blocked by this circle, then the radius of this circle that blocks triangle ABC will be equal to A times B times C, that is the multiplication of the side lengths of the triangle by each other, over 4 times the area of this triangle. So we actually can implement this rule number 1 in our drawing. Right? Because of the fact that in our drawing we have triangle BDF, the green triangle, triangle triangle BDC, the green triangle BDC is blocked by this circle. Why it is blocked by this circle? Because of the fact that all the three vertices of the triangles lying on the circle. Here, this is the first vertex that touches the circle at point B. The second vertex, this is the second vertex of the triangle, the green triangle that touches the circle at point C, and finally we have the third vertex that touches of the triangle that touches the circle at points D. Therefore, we can say the triangle BDC is blocked by the circle. Why? Because all the three vertices are touching the circles at different points. Okay? So it means that we can use rule number 1 in our drawing. Okay? And therefore, so I'll write it down. Triangle, the green triangle BDC is blocked by the circle. Why? Because all three vertices touching the points on the circle itself, and therefore the radius of this circle, so we define the radius of this circle here, O is the center of the circle, M is the point of the circle itself, therefore OM is the radius of the circle. We define the radius of the circle as capital R. So the radius of this circle, capital R, will be equal to the multiplication of the side lengths of the triangle BDC by each other. That is to say, it is side BC times side DC times the length of side DB over 4 times the area of triangle BDC. Okay, I repeat again. Because of the fact that triangle BDC is blocked by the circle. Why? Because all the three vertices of this green triangle are touching the circle at different points. So, because of the fact that this circle blocks triangle BDC, we can use here rule number 1. And according to rule number 1, the radius of this circle that blocks the green triangle, that is to say capital R, will be equal to the length of side BC times the length of side DC times the length of side DB over 4 times the area of the green triangle. So capital R equals to BC. The length of side BC is equals to 13 units according to what is given us in the question. Times the length DC. We've already found out that the length of side DC equals to the root of 61 units times the length of the side DB, that is equal to 6 times square root of 10. All divided to 4 times the area of triangle BDC. And we already found out that the area of triangle BDC equals to 39 square units. Here we have already found out that the area of triangle BDC equals to 39 square units. So it is 4 times 39. So the radius of this circle that blocks the green triangle BDC will be equal to this expression. So here we will divide both the numerator and the denominator by 13. 13 over 13 is 1, so 13 will get cancelled. We left only with square root of 61 times square root of 10 times 6. In the denominator we have 4 times 39. So we divide 39 by 13 because we divided both the numerator and the denominator by 13. 39 over 13 is 3. Okay. Now we will divide both the numerator and the denominator of this expression by 6. 6 over 6 is 1, so 6 will get cancelled, and we left in the numerator only with 60 square root of 61 times square root of 10. All divided by 4 times 3. 4 times 3 is 13, and 13 over 6 is 2. Okay, so we found out that the radius of this circle that blocks the green triangle BDC equals to the square root of 61 times square root of 10 over 2. According to the algebraic identity that square root of A times square root of B equals to the square root of A times B, we will get that the square root of 61 times square root of 10 will be equal to the square root of 61 times 10, all divided by 2. So the radius of the circle, this circle that blocks the green triangle BDC, will be equal to the square root of 61 times 10 is 610 over 2 units. In terms of numbers, it is equal to 12.349 units. Okay, so we finished with the first method. Again, the radius of this circle that blocks the green triangle equals to either the square root of 610 over 2, or in terms of numbers, it is equal to 12.349 units. Okay. In the next step, I will present to you the second method to find out the radius of this circle. Actually, in order to shorten this lecture, I will not repeat on the same thing that I already done, that I already did in the first method. BC equals to 13 units, AD equals to 13 units. So here, from point C, we draw perpendicular on AD. We already found out that this equals to 6 units. Here, this angle, it is also equals to 90 degrees. Therefore, quadrilateral AB EC is a rectangle, and the opposite sides of the rectangle are equal to each other. That is to say, AB equals to EC equals to 6, and AE equals to BC equals to 13, and ED equals to 5. Okay? All these things we have already done in the first method, so I will not repeat on it. And in the next step, from point O, that is the center of the circle, we will draw perpendicular on chord BC. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and BC as point N. We will define the touching point of the perpendicular from point O and AD as point M. In the next step, I will present to you a new rule, and we implement the new rule in our drawing. This will be rule number 3. According to rule number 3, Rule number 3 is true in any circle. If we have this circle and we know that the center of this circle is at this point, point O. And then we have here chord AB. AB is chord, the chord of in this circle. And from point O we'll go perpendicular on AB. That is to say, here this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We'll define the touching point of the perpendicular from point O and AB as D. According to rule number 3, the perpendicular from the center of the circle, that is to say from point O to chord AB, that could be any chord, bisect the chord. That is to say, AD equals to DB. I repeat again, in any circle, if we have chord AB that could be any chord, when we draw perpendicular on the chord AB, the perpendicular on chord AB bisects chord AB, that is to say AD equals to DB. We can actually implement rule number 3 in our drawing. Why? Because in our drawing we have chord BC, this is chord BC, and from the center of the circle, that is to say from point O, we have perpendicular ON. Here this angle equals to 90 degrees and this angle equals to 90 degrees. So I write it down. From the center of the circle we have line segment ON, is perpendicular to chord BC. Okay. Again, line segment ON that exists from the center of the circle is perpendicular to chord BC. Therefore, according to rule number 3, we'll get that line segment ON bisects BC. That is to say, BN equals to NC. BN equals to NC. BN equals to NC according to the new rule, rule number 3. Okay. Again, because of the fact that line segment ON is perpendicular to chord BC, according to rule number 3, the perpendicular from the center, that is to say ON, bisects chord BC. That is to say BN equals to NC. Okay. In the next step, we will focus on quadrilateral ABMN. This quadrilateral. In this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. And because of the fact that quadrilateral ABMN has 4 right angles, quadrilateral ABMN is at least a rectangle. Quadrilateral ABMN is a rectangle. Why? Because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. AM equals to BN in rectangle ABMN. Okay? Likewise, we'll focus on quadrilateral MNEC. Quadrilateral MNEC. In quadrilateral MNEC, this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees, and therefore quadrilateral MNEC is at least a rectangle, if not a square, so we will relate to quadrilateral MNEC as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides in this rectangle MNEC, they are equal to each other. That is to say, ME equals to NC. ME equals to NC. Okay? So, actually, you can summarize and say that according to rule number 3, we have already found out that BN equals to NC. According to rule number 3, this equation is true from one side. But from the other side, we also found out that BN equals to AM. So we can write here that BN equals to AM. And we also found out that NC equals to ME. So we can write here that NC equals to ME. So from this long equation, we will derive that AM equals to ME. AM equals to ME. Okay? AM equals to ME. Okay? In the next step, we'll extend line segment AD towards the upper side of the circle until it touches the circle. And we will define the touching point of the extended line segment AD and the circle as point F. Okay, actually we created here chord FD. Okay, we have here chord FD. We'll focus ON is perpendicular to BC. ON is perpendicular, it is absolutely a straight line. ON is a straight line. So if we focus on the upper side of the straight line ON at point M, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. The sum of the angles on one side of a straight line is equal to 180 degrees. I'll not repeat on this rule. So, which angles we have at the upper side of the straight line ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle here must be equal to 90 degrees in order to complete the sum of the angles on the upper side of the straight line ON at point M to 180 degrees. The missing angle must be also equal to 90 degrees. Likewise, if we focus on the lower side of the straight line ON at point M, here also the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have at the lower side of the straight line ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees according to the rule that I mentioned. So actually we found out that here we have OM is perpendicular to chord FD. Why? Because this angle equals to 90 degrees and this angle equals to 90 degrees. So I'll write it down Actually, in our original drawing, we have line segment OM that starts from the center of the circle, that is to say from point O, is perpendicular to chord FD. Okay? Repeat again. Line segment OM that exists from the center of the circle, that is to say from point O, is perpendicular to chord FD. Therefore, we can implement here rule number 3. Therefore, according to rule number 3, line segment OM bisects chord FD. According to rule number 3, that is to say FM equals to MD. FM equals to MD according to rule number 3. Okay? FM equals to MD. Here FM equals to MD because of the fact that OM bisects chord FD. What is the value of FM? From the drawing it is very easy to see that FM equals to FA plus AM. FA plus AM what is the value of MD? MD, it is very easy to see from the drawing that MD equals to ME plus ED. ME plus ED. So in conclusion, we found out that FM that equals to MD, actually FM equals to FA plus AM, and it equals to MD, but MD equals to ME plus ED. But we have already found out that AM equals to ME. Yeah, we already found out that AM equals to ME. Therefore, we can cancel AM and ME because they are equal to each other. And we left only with FA that is equal to ED. FA equals to ED. FA equals to ED. But we have already found out that ED equals to 5 units. So we can write here that ED equals to 5 units. And from this equation FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. FA equals to 5 units. Okay. In the next step, we will extend line segment BA until it touches the circle and we will define the touching point of the extended line segment BA and the circle is point P. Actually, I've already mentioned rule number 2, so I'll not repeat on it. According to rule number 2 that is true in any circle, if we have chord AB that intersects with chord CD at point O, then AO times OB equals to CO times OD. Okay? And this is true in any circle. So we can implement rule number 2 in our drawing. Why? Because in our drawing we have chord FD, this is chord FD, that intersects with chord DB at point A. I write it down, chord FD intersects with chord BD, is called in the intersection point occurs at point A. At point A. Therefore, according to rule number 2, we'll get that FA times AD, FA times AD equals to BA times AP, equals to BA times AP. Repeat again, because of the fact that chord FD intersects with chord, actually it is called BP, chord FD intersects with chord BP, again chord FD intersects with chord BP, this is called BP or PP at point A. Therefore, according to rule number 2, we get that FA times AD equals to BA times AP. FA equals to 5, AD equals to 18, and this is equal to BA. BA equals to 6, and AP is the missing 9 segment, so we leave it as it is. So in conclusion, according to rule number 2, we found out that 5 times 18 equals to 6 times AP. Here we will divide this equation by 6, and we will get that the missing 9 segment AP equals to 5 times 18 over 6. Here 18 over 6 is 3, and 3 times 5 is 15. So we actually found out that AP equals to 15 units. We can write down that AP equals to 15 units. AP equals to 15 units. In the next step, I will present to you a new rule that we will implement the new rule in our drawing. This will be rule number 4. Rule number 4 is drawing any circle. So if we have this circle, that will be any circle. In this circle we have chord AB, this is chord AB. This is chord AB that intersects with chord CD. This is called CD. And the angle between the two chords that create with each other, angle of 90 degrees, at 90 degrees. And the intersection point occurs at point O. I write it down. If chord AB intersects with chord CD at 90 degrees, that is to say they create with each other 90 degrees at the intersection point here, and the intersection point occurs at this point, point O, then the following equation will be true. If the radius of this circle is equal to capital R, here the center of the circle is at this point. So here The center of the circle will be defined as point C, as point E, and the point on the circle itself is point M. So Cm is the radius of this circle that is equal to capital R. So here, if we know that chord AB intersects with chord CD at 90 degrees, then 4 times R squared, that is to say R is the radius of this circle, is equal to AO squared plus OB squared plus CO squared plus OD squared. Okay? Repeat again, if chord AB intersects with chord CD at 90 degrees at point O, then for R squared, R is the capital R is the radius of this circle, it will be equal to AO squared plus BO squared plus CO squared plus DO squared. So we actually can implement rule number 4 in our drawing. Why? Because in our drawing we have chord FD, chord FD, this chord intersects with chord PB, this is called PB, at 90 degrees. Here the intersection point between the two chords creates 90 degrees. They create between them 90 degrees here. This area equals 90 degrees at point A. Repeat again, chord FD intersects with chord PB at 90 degrees at point O. Therefore, according to rule number 4, we get that for R squared, R is the capital R is the radius of this circle. Equals to capital R. Capital R is the radius of the circle. 4R squared equals to FA squared plus AD squared plus PA squared plus AB squared. Repeat again. In our original drawing, chord FD intersects with chord PB at 90 degrees, therefore we can implement here rule number 4. Any two chords that intersect with each other at 90 degrees, whenever we have such a reality, then we can actually implement rule number 4. According to rule number 4, 4R squared equals to FA squared plus AD squared plus PA squared plus AB squared. So 4R squared, R is the radius of the circle, or capital R is the radius of the circle. It is equal to FA squared. FA equals to 5, therefore FA squared equals to 25 plus AD squared. AD equals to 18, therefore AD squared equals to 18 squared, that is 324, plus PA squared. PA equals to 15, so PA squared equals to 15 squared, that is 225, plus AB squared. AB equals to 6, so AB squared equals to 6 squared, that is 36. So in conclusion, we found out that 4R squared equals to 25 plus 324 plus 225 plus 36. So 4R squared equals to 25 plus 225 is 250, and 324 plus 36 is 360. In conclusion, we found out that 4R squared equals to 250 plus 360, that is actually 610. Here we divide this equation by 4 and we get that R squared equals to 610 over 4. Here we take a root out of this equation and we will get that capital R equals to the square root of 610 over 4. Here we can take 4 out of this root. Why? Because the square root of 4 is 2. So in conclusion, we get that capital R equals to the square root of 610 over the square root of 4, that is 2. So we found out that the radius of this circle, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay? In the next step, I will summarize the lecture. And we'll start with the first method. So here in the drawing we have a circle. Inside this circle we have line segment AB that is equal to 6 units, line segment AD equals to 18 units, line segment BC equals to 13 units, angle BAD equals to 90 degrees, angle ABC equals to 90 degrees, and our mission is to find out the radius of this circle. Okay, the center of the circle is point O, and we want to find out the value of OM, that is the radius of this circle. Okay, so first of all, from point C, we draw perpendicular on AD. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point C and AD as point SE. So here, we actually created here quadrilateral by this construction. We created quadrilateral ABEC. In quadrilateral ABC we have 1, 2, 3 right angles, therefore the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And because of the fact that all the angles inside quadrilateral ABEC are right angles, therefore quadrilateral ABEC is a rectangle. Okay? And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But we know that AB equals to 6 units, therefore EC also equals to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we know that AE equals to BC. But we know, it is given us the equation that BC equals to 13 units. Therefore, AE must be also equal to 13 units. Then what is the value of ED? ED equals to AD minus AE. That is to say, ED equals to AD, that is 18, minus AE, that is 13. 18 minus 13 is 5. So DE equals to 5 units. In the next step, we join points D and C together by a straight line. By joining points D and C, we created the small right triangle EDC. So here we can implement the Pythagoras theorem of the small right triangle EDC. In the small right triangle EDC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is DC, therefore the square of the hypotenuse is DC square. DC square must be equal to the sum of the squares of the perpendiculars. This is to say it must be equal to EC square plus ED square. Must be equal to EC square plus ED square. So DC square, that is the square of the hypotenuse, must be equal to EC square. EC equals to 6, therefore EC square equals to 6 squared, that is 36, plus ED square. ED equals to 5, therefore ED square equals to 5 squared, that is 25. In conclusion, we found out that DC square equals to 36 plus 25. 36 plus 25 is 61. That is to say, we found out that DC square equals to 61. We took a root out of this equation and found out that DC, the hypotenuse DC, equals to the square root of 61 units. Then we joined points B and D together by a straight line. By joining points B and D, we created here the right triangle ABD. Then we implemented the Pythagoras theorem on this right triangle ABD. Triangle ABD. Okay. According by PT as an expression for Pythagoras theorem, the square of the hypotenuse is BD square and must be equal to AB square plus AD square. BD square equals to AB square plus AD square. So BD square equals to AB square. AB equals to 6, therefore AB square equals to 6 squared, that is 36, plus AD square. AD equals to 18, therefore AD square equals to 18 squared, that is 324. So in conclusion, we found out that BD square equals to 36 plus 324. 36 plus 324 is 360. So in conclusion, we found out that BD square equals to 360. We took a root out of this equation and found, so here, before that BD square equals to 360, but 360 is 36 times 10, of course. So we substitute 360 by 36 times 10, so we found out that BD square equals to 36 times 10. We took a root of this equation and found out that BD equals to the square root of 36 times 10. The square root of 36 is 6, so we can take out 36 out of the root. And inside the root, we left only with square root of 10. In conclusion, we found out that BD equals to the hypotenuse BD of this right triangle equals to 6 times square root of 10 units. Okay? And then we found out the area of the green triangle BDC. The area of this triangle BDC. The area of any triangle, and the special triangle BDC, equals to the base of the triangle times the height to the base over 2. I will emphasize that the height to the base must create 90 degrees with the base. Okay, so the area of any triangle, and especially triangle BDC, equals to the base of the triangle times the height to the base over 2. Okay, so here the area of the green triangle will be equal to the base. We choose the base as BC. This is the base, and the height to the base must create 90 degrees with the base BC. With the base BC or with the extended BC. So we actually extended side BC by a straight line, and from point D we do perpendicular on the extended BC. Therefore, here DF that creates 90 degrees with the extended BC, it is the height to the base BC. Okay? And we'll focus on quadrangle A. Here we define the touching point of the perpendicular from point D and the extended BC as F. We'll focus on the quadrangle ABDF. This quadrangle, in quadrangle ABDF, we have 1, 2, 3 right angles. Therefore, the fourth angle, this angle must be also equal to 90 degrees, and therefore quadrangle ABDF that has 4 right angles, it is a rectangle. We will relate to quadrangle ABDF is a rectangle. It is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in the rectangle ABDF, AB equals to DF. AB equals to DF. What it is given us the equation that AB equals to 6 units. So from this equation 6 equals to AB equals to DF, we will derive that DF is also equals to 6 units. Here DF equals to 6 units. Okay, so now we can calculate the area of the green triangle BDC. Again, the area of the green triangle BC, the squared brackets is the sign for the area. The area of the green triangle BDC equals to the base of the triangle times the height to the base over 2. The base is BC, and BC equals to 13. So we substituted the base by 13. The height to the base is DF, and DF equals to 6, so we substituted the height by 6. So it is 13 times 6 over 2. That is the area of the green triangle BDC. 6 over 2 is 3, so in total this expression equals to 13 times 3. 13 times 3 is 39. In conclusion, we found out that the area of the green triangle BDC equals to 39 square units. Okay? The area of this green triangle equals to 39 square units. Then I presented to you a new rule, and we implemented the new rule in our drawing. Here, according to rule number 1, if a triangle is blocked by a circle, like here we have triangle ABC that is blocked by this circle. That is to say, what is the meaning of blocked? It means that all 3 vertices of triangle ABC touching the circle. You can see here. And so here we can see the triangle ABC is blocked by this circle, and then the radius of this circle that blocks triangle ABC, here we know that the length of side AB equals to A units, side BC equals to B units in its length, and side AC equals to C units in its length. Then the radius of this circle that is blocked, the radius of this circle that blocks triangle ABC, if we define the radius of this circle OM as capital R, then capital R will be equal to A times B times C, that is the multiplication of the side lengths of this triangle, A times B times C, over 4 times the area of triangle ABC that is blocked by the circle. So we actually can implement this rule number 1 in our drawing. Why? Because in our drawing we have the green triangle BDC that is blocked by this circle. Why the green triangle is blocked by this circle? Because of the fact that all 3 vertices of this triangle touching the circle. This vertex touches the circle at point B. This vertex touches the circle at point C, and finally this vertex touches the circle at point D. Therefore, we can conclude from it that indeed the green triangle BDC is blocked by this circle, and therefore we can implement here rule number 1. Okay, and according to rule number 1, the radius of this circle, that is to say OM, that is capital R, we define the radius of this circle as capital R, will be equal to the multiplication of the length of the 3 sides of the green triangle times over 3 times the area of the green triangle. I repeat again. Triangle BDC is blocked by the circle. Why? Because all 3 vertices of the triangle touching the circle at different points. Therefore, we can implement rule number 1. According to rule number 1, the radius of the circle that blocks triangle BDC will be equal to the multiplication of the side lengths of the triangle The length of this side is BC. The length of this side is CD, and the length of this side is BD. Okay, so it is BC times DC times BD or DB. It's the same. It is the multiplication of the three sides, the multiplication of the sides lengths of the triangle by each other over 4 times the area of this triangle BDC. BC equals to 13 units, DC equals to the square root of 61, and BD equals to the 6 times square root of 10 units. Okay, BC equals to 13, DC equals to the square root of 61, and BD equals to 6 times square root of 10 units over 4 times the area of triangle BDC. And we have already found out that the area of the green triangle BDC equals to 39 square units. Okay, so here we divided both the numerator and the denominator of this expression by 13. Here 13 over 13 is 1, so 13 will get cancelled, and we left in the numerator only with square root of 61 times square root of 10 times 6. In the denominator we have 4 times 39. 39 divided by 13 is 3. So in conclusion, in the denominator we have 4 times 3. Then we divided both the numerator and the denominator of this expression by 6. 6 over 6 is 6, so 6 will get cancelled. In the denominator we have 4 times 3, that is 12. So 12 over 6 is 2. So in conclusion, we found out that the radius of the circle that blocks triangle BDC equals to square root of 61 times square root of 10 over 2, because 12 over 6 is 2. Okay, and according to the algebraic identity that the square root of A times square root of B equals to the square root of AB, we will get that the square root of 61 times square root of 10 will be equal to the square root of 61 times 10, all divided by 2. 61 times 10 is 610, so inside the root we have 610 over 2. So we actually found out that the radius of this circle, according to the first method, equals to either the square root of 61 over 2 units, or in terms of numbers, it is equal to 12.349 units. We finished with the first method, then I presented to you the second method. Here I will not repeat on the same thing that I've already done in the first method. Here from point C we draw perpendicular on AD, therefore this angle equals 90 degrees, this angle equals 90 degrees. We have already found out that EC equals to 6 units, and AE equals to 13 units. Why? Because of the fact that ABEC is a rectangle and ED equals to 5 units. Okay? Then from point O, that is the center of the circle, we draw perpendicular on chord BC. Okay, from point O we draw perpendicular on chord BC. We define the touching point of the perpendicular from point O, that is the center of the circle, on BC as N, capital N. And then I presented to you in the rule, that is actually rule number 3. According to the rule number 3, if we have in this circle chord AB, that could be any chord, and from the center of the circle we draw perpendicular on chord AD, on chord AB. From point O we draw perpendicular on chord AB. We define the touching point of the perpendicular from point O and AB is D, then this perpendicular, so this angle equals 90 degrees and this angle equals 90 degrees according to our construction. But the perpendicular OD is not only perpendicular to the chord AB, but it is also bisect AB. That is to say, AD equals to DB. According to the new rule, the perpendicular from the center of the circle to a chord bisects the chord. So the perpendicular OD bisects chord AB, that is to say AD equals to DB. We can actually implement rule number 3 in our drawing. Why? Because we have here the perpendicular ON bisects chord BC. That is to say, BN equals to NC according to rule number 3. Okay? According line segment ON, that is the perpendicular from the center, is perpendicular to BC, and therefore according to rule number 3, BN equals to NC. BN equals to NC. Okay? So we'll focus on quadrilateral AB and M. This quadrilateral, in this quadrilateral we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. And because of the fact that quadrilateral AB and M has 4 right angles, quadrilateral AB and M must be at least a rectangle if not a square, so we relate to quadrilateral AB MN as a rectangle. Again, quadrilateral ABMN is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say AB, and that is to say BN equals to AM. BN equals to AM according to the rule that the opposite sides of a rectangle are equal to each other. Then we focus on quadrilateral, the lower quadrilateral MN EC. In quadrilateral MNEC, this quadrilateral, we have here 1, actually here 1, 2, 3 right angles. Why? Because here we know that AD is a straight line, so if this angle equals to 90 degrees, this angle must be also equal to 90 degrees. The same thing is true here on chord BC is a straight line, of course. In chord BC, this angle equals to 90 degrees, so this angle must be also equal to 90 degrees. And from point C, we draw perpendicular on AD. So in conclusion, we can say that we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. And because of the fact that quadrilateral MNEC has 4 right angles, quadrilateral MNEC is a rectangle. Okay, quadrilateral MNEC is a rectangle because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. Okay, so in conclusion, according to rule number 3, we found out that BN equals to NC. But we already found out that BN also equals to AM. So we can write here that BN equals to AM. And we have already found out that NC, here, NC equals to EM. So we can write here that NC equals to EM. And from this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. Here we can write here that AM equals to ME. Okay? In the next step, we extended line segment AD by a straight line until it touches the circle at point F. We actually created here chord FD or DF. Okay, we have chord FD, and from point O we have perpendicular on BC, yes? So here this is a rectangle, and we know that ON is perpendicular, it is absolutely a straight line. And we know that the sum of the angles on one side of a straight line must be equal to 180 degrees. So if we focus on the upper side of the straight line ON at point M, which angles we have here, this angle equals to 90 degrees, plus the missing angle, in total they must be equal to 180 degrees. Therefore the missing angle must be equal to 180 degrees in order to complete the sum of the angles on the upper side of ON at point M to 180 degrees. The missing angle must be equal to 90 degrees. Likewise, if we focus on the lower side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees. So which angles we have at the lower side of OM at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle must be also equal to 90 degrees. Okay, so I actually found out that from the center of this circle, we have perpendicular on FD. OM is perpendicular to FD. Why? Because this angle equals to 90 degrees and this angle equals to 90 degrees. Therefore, we can implement here rule number 3. Because of the fact that line segment OM is perpendicular to chord FD, we can implement here rule number 3. And according to rule number 3, the perpendicular OM bisects chord FD. That is to say, FM equals to MD. Okay? Because of the fact that OM is perpendicular to FD, we will derive that according from rule number 3, that FM equals to MD. But what is the value of FM? FM equals to FA plus AM. FA plus AM. And what is the value of MD? For the domain, it is very easy to see that MD equals to ME plus ED. MD equals to ME plus ED. So here FM equals to FA plus AM, and it is equal to MD, that is equal to ME plus ED. So those two sides are equal to each other. But because of the fact that AM equals to ME, we have already found out that AM equals to ME. We can cancel them. So we can subtract them from the equation because they are equal to each other. And we left only with FA, that is equal to ED. FA equals to ED. Here FA equals to ED. But we know that ED equals to 5 units. So we can write here that ED equals to 5 units. And from this equation FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. Here FA equals to 5 units. Then, according to the rule that I have already presented to you, actually we have the rule that says if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. We can implement the new rule, the old rule, in our drawing. Why? Because in our drawing we have chord F. We actually extended line segment BA until it touches the circle at point P. Okay? So here we implemented the old rule in our drawing. We have chord FD that intersects with chord BP at point A. Repeat again. We have chord FD that intersects with chord BP at point A. Therefore, according to the old rule, rule number 2, we get that FA times AD equals to BA times AP. Repeat again, according to rule number 2, FA times AD equals to BA times AP. Okay? Again, chord FD intersects with chord BP at point A, therefore FA times AD equals to BA times AP. FA times AD equals to BA times AP. FA equals to 5, AD equals to 18, BA equals to 6, and AP is the missing 9 segment. So in conclusion, we found out that 5 times 18 equals to 6 times AP. We divided this equation by 6 and we found out that AP equals to 5 times 18 over 6. 18 over 6 is 3, so in total this expression equals to 3 times 5, that is 15. In conclusion, we found out that AP equals to 15 units. Here AP equals to 15 units. In the next step I presented to you rule number 4 and we implemented rule number 4 in our drawing. According to rule number 4, if we have chord AB, this is chord AB that intersects with chord CD, this is chord CD, and they intersect with each other. In the intersection point, they create between them 90 degrees at point O. Then if this is the reality that we have in the circle, and we also know that the radius of this circle CM equals to capital R, then the following equation is true. The 4 times R square, R is the radius of this circle, or capital R, equals to AO square plus OB square plus CO square plus OD square. Again, 4 times R square equals to AO square plus OB square plus CO square plus OD square. We can actually implement rule number 4 in our drawing. Why? Because in our drawing we have chord DF, this is chord DF, that intersects with chord PB at point A. I'll repeat again, chord DF intersects with chord PB at point A at 90 degrees. Here, this angle equals to 90 degrees. That is to say, they create between them 90 degrees at the intersection points. Therefore, we can implement here rule number 4. According to rule number 4, we'll get that 4 times R square, R is the radius of the circle, will be equal to FA square plus AD square plus BA square plus AB square. According to rule number 4, we'll get that 4R square equals to FA square plus AD square plus BA square plus AB square. Okay, so 4R square equals to FA square. FA equals to 5, therefore FA square equals to 5 square, that is 25, plus AD square. AD equals to 18, therefore AD square is 18 square, that is 324. Plus PA square. PA equals to 15, therefore PA square equals to 15 square, that is 225. Plus AB square. AB equals to 6, therefore AB square equals to 6 square, that is 36. In conclusion, found out that 4R square equals to 25 plus 324 plus 225 plus 36. That is to say, 4R square equals to 25 plus 225 is 250, and 324 plus 36 is 360. In conclusion, found out that 4R square equals to 250 plus 360. 250 plus 360 is 610. That is to say, we found out in conclusion that 4R square equals to 610. We divided this equation by 4 and we got that R square equals to 610 over 4. Then we took a root out of this equation and we got that the R equals to the square root of 610 over 4. The square root of 4 is 2. So in conclusion, we found out that the radius of this circle is equal to the square root of 610 over square root of 4, that is 2. So in conclusion, we found out that the radius of this circle equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay? And that is the answer to the question according to the second method. Okay, thank you very much.